How's it going, everybody? Professor Bryant back. Today's lecture video is going to be covering Chapter 3, which is Module B. And we're going to be talking about chemical reactions and reaction stoichiometry. What I'm going to try to do with this video is incorporate the in-class worksheet along with the PowerPoint. So the video may be a little bit longer, but what we're going to try to do is, as we cover the kind of content within the lecture component, we're going to also look at the examples on the in-class worksheet along with the video. So chapter 3 is a kind of merging of chemical reactions and prior content, really kind of basic level content that you should remember from the prerequisite course, and reaction stoichiometry at this level of the chemistry 1411. So stoichiometry sounds like, it's a confusing word. It sounds a little intimidating, but really all stoichiometry looks at is how much did you use up in a chemical reaction and how much did you make, and how those two amounts are related, right? They are proportional. They are going to always be proportional regardless of what kind of chemical work that you're doing. So Antoine Lavoisier, long time ago, he did some work with some chemicals, particularly gases, and he was able to essentially come up with the idea that the law of conservation of mass, meaning that you will not create or destroy mass in a chemical process, you will just change its form, but you will always still have that exact same amount of mass at the end. And that's what he is saying below here in this quote. So when we talk about chemical equations, we are talking about the basic formatting that we will be using throughout all of your chemistry courses on how to represent the reaction on paper when you're writing it. So when we have an arrow, the arrow separates the reactants or the elements and compounds that's on the left of the reaction, or what we start with, from what is produced, or the products, and that's why we call them products. If you see a plus symbol, that is what separates different entities, whether they be elements or compounds. So if you have multiple reactants, you should see plus sign. If you have multiple products, you will also see plus sign. Now, because of the law of conservation of mass, we must balance equations by balancing the amount of any particular element on both sides of our arrow, meaning that we cannot have one atom of carbon on the left side and no atoms of carbon on the right side. It does not follow that law. So what we must do is, by looking at the coefficients, which are the numbers that we see right here in the front, looking at the coefficients, we can determine how many are on each side, and we can utilize that to kind of balance them. And we'll show some balancing examples in the in-class worksheet. But we do not balance using the subscripts. We use whole numbers that are to the left of the element or compound. Now, sometimes this is a check and try again method. Sometimes you have to experiment with different numbers. It's not going to always be straightforward in the balancing. Sometimes it's going to take multiple different attempts. So what we see here is the combustion reaction involving methane and oxygen to produce carbon dioxide and water, which are always the products of a combustion of a hydrocarbon or a carbohydrate. So we see here 2 times 2 is 4, and we see that we have 2 oxygens here and we have 2 oxygens here, because this coefficient in the front is always multiplied by the subscript, or multiplied by 1 if there is no subscript. And the reason why we use the coefficient instead of the subscript is because a subscript will change the identity of the compound or element, and we do not want to do that. We want to change the amount of a specific compound or element, not change its identity. We do not want to change the identity. Sorry about that. Okay, so there are some other symbols that you will see placed into chemical equations. Small italicized letters in parentheses such as G, L, and S are going to be representing gas, solids, or liquids, or gas, liquids, or solids. And then if you see a AQ, that means that something has been dissolved in aqueous solution or dissolved in water. I will be asking you for most of this course to make sure that you have your phases or your states of matter written on your chemical equations. As you can see here, this is a completely gaseous reaction, combustion of methane, oxygen gas to create carbon dioxide and water. Now that triangle there, delta, means that you're going to have some heat released. And you will need heat present for the reaction to take place. So there are types of reactions that we're going to see pretty consistently amongst all chemistry, and they kind of fall into a couple different buckets, if you will. Combination reactions, or sometimes heard as synthesis reactions, involve taking two compounds or two elements, or one compound and one element, and creating something. Decomposition reactions involve taking an element or a compound and decomposing it. Most of the time you're going to see this in a compound decomposing. And then combustion reactions, which is the example that we just used, is burning something in air or in oxygen. So we talk about combination reactions, two or more substances, and it could be any number of substances, but two or more react to form a singular product, right? A singular product. So a combination and decomposition reaction are shown here in the generic format. A plus B gives us C, and we see here solid carbon and oxygen create CO2. We have the Haber process, which is gaseous nitrogen, gaseous hydrogen to create ammonia gas. Very important industrial process for life on this planet. And then we have calcium oxide and water to form calcium hydroxide aqueous. Notice we have phases on all of these, and also notice that all of these are already balanced. You may get situations where you have to balance, and we're going to see that on the in-class worksheet. So you should be able to predict the product of a combination between a metal and a non-combination reaction, because the common charges for the groups, and we should remember and realize that we are dealing with ionic compounds when metals are interacting with non-metals. So you should be able to predict the product of this reaction because of common charges, and because you should know that it is an ionic reaction. And we're going to see some examples of that too. So in a decomposition reaction, one substance, whether it's a compound or a salt, if you will, it could be a solid, could be a gas, but they break down into two or more substances. So it's kind of the reverse of a combination, a reverse of a synthesis reaction. So what we see here is C breaking down into A and B, and we have that here. We have potassium chlorate breaking down into potassium chloride and oxygen, lead carbonate or lead 2 carbonate breaking down into lead 2 oxide and carbon dioxide, and then copper hydroxide breaking down into copper oxide and water. A real life example of this, sodium azide releases nitrogen gas quickly because sodium azide breaks down into nitrogen gas, and that is where the airbag deploys, and that is why it fills up with air, or fills up with nitrogen specifically. So metal carbonates generally decompose if you heat them up and you give off the metal oxide and the CO2, carbon dioxide gas. So when we balance these equations, you balance them based on the charge of the metal in your reactant. Remember, left is reactant, right products. So in this case, calcium is calcium 2. Why? Because it's in group 2. but its calcium has a 2+ charge because it's in group 2. Therefore, it's going to keep a 2+ charge. It's in group 2. And oxygen has a 2- charge because of its position on the periodic table and carbon dioxide. And then combustion reactions that we're familiar with lighters. In this case, they're showing you a propane torch. Rapid reactions that produce a flame. They most often involve oxygen in the air as the reactant. In this case, they show you propane, C3H8, burning in oxygen to create CO2 and water. And we've seen this. We've seen the phases. We've seen the balancing. And we will see this time and time again. So let's go to our in-class worksheet. So if we look at the in-class worksheet here, and we can zoom in here and get a little closer. What we have here is strontium solid and oxygen gas to create strontium oxide. And we notice that we have a plus in between these two. These are the reactants, remember. We have an arrow giving us a single product, and we're already balanced here, and we've been asked to determine the type of reaction. This is going to be a combination, or you can write this as a synthesis. Okay? So this will be an example of being able to designate the type for the reaction. Now let's take a look at this next one. We have C8H18, which is octane, which is what we put in our vehicles, gasoline vehicles, that is. We have oxygen, we have CO2 and water. Now notice that this reaction is not balanced. What we end up having to do to balance it is put a 2 here. We end up having to put a 18 in front of water. We end up having to put a 16 in front of CO2. And we end up having to put a 25 in front of oxygen if we needed to balance it, right? We don't need to have it balanced to answer the question, but this is a combustion. And I should write combination up here so we don't get confused. And then the next one is the calcium carbonate that we have seen in the slides, and we see and we know that this should be a decomposition reaction. Okay, now question 2, let's look at balancing. We just balanced up here, but let's do it again. I suggest for all your combustion reactions to always leave oxygen as the last thing that you balance. Always leave oxygen as the last thing. I normally start with carbon, and we see that we need carbon could be 4, but I also look at hydrogen, because if the hydrogen value here, if we need an odd number in front to create the number of hydrogens, we're not going to get an odd number of oxygen ever over here because we have 2 oxygens. So what I always suggest is if we have an odd number here, we always double this. And then we balance the carbons using an 8. From there, we see we have 20 hydrogens, so we need a 10 here. And now we see we have 16 and 10, which is 26, so that we need 13 moles of O2, 13 moles. And now here we have what is known as a double replacement reaction, okay? And we're going to talk about this a little bit more in the aqueous reaction, but this is a double replacement, which is known as a kind of swapping of partners here. And this double replacement reaction is balanced by utilizing a 2 here, by utilizing a 3 here, by utilizing a 6, and there's just a 1 here, and we don't need to put that 1, but you can if you want to. Now, you can pause the video and convince yourself that you can solve this, because I'm not going to go through that step by step, but make sure that you can still balance an equation with the lowest common multiples of any type of equation that could be thrown at you. Okay, so now if we go back to the slides, formula weight. So when we're talking about formula weight, and we're kind of switching gears because now we're talking about the chemical formula itself, whether we're dealing with an element or a compound. The formula weight is the sum of the atomic weights in the chemical formula. So we're talking about atomic weights. We're talking about the value on the periodic table underneath the chemical symbol. This is quantitative, meaning this is a mathematical value that is very significant in all of our work from here on out, pretty much in this course. So you always need to be able to solve for the formula weight. You also may see that as molecular weight. They are interchangeable definitions. So for an element like sodium, the formula weight is the atomic weight, 23.0 AMUs. And that's also utilized in grams per mole as well. Now, for an ionic compound, you are always going to use the empirical formula, and we'll talk a little bit more about empirical formulas as well. And then the formula weight of a covalent compound, such as sulfuric acid, H2SO4, will be 2 times the atomic weight of hydrogen, 1 time the atomic weight of sulfur, and 4 times the atomic weight of oxygen. And they show you the math here, and they show you how to calculate the formula weight. The molecular weight is if the substance is a molecule, then the formula weight will also be called its molecular weight. And what is a molecule? A molecule is one or more atoms, right? If it is a elemental molecule, it will be one or more of the same atom, right? So molecular weight is the sum of the atomic weights of the atoms in a molecule, and glucose, which we see here, is sugar, and we see how they have solved for the molecular weight of sugar. And we're going to do some practice on that as well. Now, one thing that chemists can sometimes be interested in, especially if they're dealing with a new compound or they found some new natural product from a plant or something of that nature, then they could be worried, they could be concerned with the percent composition. How much oxygen is in this molecule? How much nitrogen is in this molecule? And we can find the percent composition by finding the percentage of the mass of one of the elements in that compound. So the percent composition of an element is the number of atoms times the atomic weight over the formula weight of the compound, or the molecular weight, multiplied by 100. And we're going to do some examples of that as well on the workout. And here's an example they show you. They kind of walk you through that. We're going to also walk you through that in the in-class worksheet. So why is Avogadro's number important? And Avogadro's number was developed by somebody named Avogadro, and they kind of told him that he didn't know what he was talking about. But he was working with gas molecules at the time. But the atom is so very small that individual molecules and individual atoms are really tough to work with. So what we did is we decided to come up with a small but universal amount, which is based on some experimentation done by Avogadro, and that is where we come up with the idea of a mole, 1 mole. And you will see that abbreviated MOL without the E. This is the amount of particles found in exactly 12 grams of carbon-12. And we'll get into some more nuclear chemistry a little bit later, but this number, you got to know it. You need to recognize it. You need to be able to use it. It will be given to you on your reference material, but 6.02 times 10 to the 23 atoms or molecules, if we're dealing with a molecule, is the number of particles in 1 mole of any substance. It does not have to just be chemical, but it is the number of things, atoms or molecules, in 1 mole. And that 1 mole is equal to the number of grams in the formula weight or the molecular weight of a particular molecule. And that's what they've shown here. 1 molecule of H2O is the 1.01 of H2, 1.01 of hydrogen, plus 1.01 of the other hydrogen, plus 16 of the oxygen, which gives you 18 AMUs. And if we look at it at a laboratory size, at a size that we're familiar with working with, we're dealing with grams, right? So we're looking at 18 grams of water in 1 mole. Now, the molar mass is the mass of 1 mole, which is what I just stated, and we use that unit as grams per mole. And the molar mass of an element is the atomic weight from the periodic table If it's diatomic, it's twice that. If it's triatomic, it's 3 times that, and so on and so forth. And the formula weight will be the same number as the molar mass, but we just change the unit to grams per mole. And if we see what the formula weight is, and we see what the molar mass is, and we see the formula itself, we notice that still Avogadro's number can relate all of these. And that is why the mole is the preferred unit for mathematical relationships, essentially, in all of our chemistry courses. So 1 mole of atoms, ions, or molecules still contains the same amount of particles, which is Avogadro's number. The number of atoms of an element in a mole is a subscript in a formula, and you still have to multiply that by Avogadro's if necessary. When we talk about conversion, you need to take a look at some of my Workout Wednesday videos if you're not familiar with this or you don't remember this from your prior courses. But we are always going to be using conversion factors and dimensional analysis to do these conversions. To convert from grams to moles, we use molar mass. To convert from moles to formula units, we use Avogadro's number. And we're going to do some of that in the in-class worksheet as well. So before we get into determination of empirical formulas, let's go ahead and go to the worksheet, and let's look at the determination of the molecular weight of a particular compound. Here, this is a carbohydrate, right? And the percent composition of hydrogen. Well, if we calculate the molecular weight to be equal to 12.01 grams per mole times 21 plus 1.01 grams per mole times 30 plus 16 grams per mole, times 2. Now, where did I get these numbers from? All of these numbers came from the subscripts, right? I needed to multiply these numbers because they impact the overall mass, right? They impact the overall mass in our entire compound. Now, if we go and we do that math, we get 314.51 grams per mole, and that is the molecular weight, right? This is the molecular weight. This is what we're looking for. Now, the percent composition of hydrogen, however, is equal to 30.30 grams all over 314.51 grams, and this is still really grams per mole because our units are going to cancel, and this needs to be multiplied by 100, and that is equal to 9.63%. So 9.63% of our compound is hydrogen. So that is the determination of molecular weight and the percent composition done there. Okay, now determination of the name and number of moles in the sample. Well, when we talk about nomenclature, right, and this is also going to be a part of the lecture when we get into the nomenclature portion, but the number of the name here is going to be copper 1 bromite, right? You got to just remember that. And I'm going to add some videos on the nomenclature side as well. Now, to determine the number of moles, however, we need to start with what we are given, which is 7.71 times 10 to the negative 4 milligrams. And we need to convert this into moles, but we first need to convert this into grams. And that means we're dealing with 1 times 10 to the negative 3 grams. And for every 1 mole of CuBrO2, there are 175.45 grams of CuBrO2. And once we do the math here, we see that we end up with 4.39 times 10 to the negative 9 moles, or 4.39 nanomoles, right? 4.39 nanomoles. So again, this is a mass to mole conversion shown here to give you an answer of 4.39. Okay. Now, when we talk about balancing and writing a chemical reaction, and we talk about understanding stoichiometry, here's a good question that kind of brings all of that together. One, can you write the reaction of the combustion of glucose? And we see that that reaction is C6H12O6, and that's going to be a solid, plus oxygen, which is going to be a gas, which gives us CO2, which is a gas, plus water, which is a gas. Okay? So here we have the reaction. You need to be able to write all of this. Now, balancing this reaction, remember what I told you. If you have an odd number that you're going to have to put in front of hydrogen to make this value, then you want to double this. But here we don't. We can put a 6 here. So if we put a 6 here, then the next thing we need to do is balance carbon. And we do that by putting a 6 here. And now we see that we have 12 oxygens plus a 6 oxygen. That means that we have 18 oxygens. But remember, we got oxygen in the reactants in 2 places. So we need 18, but we already have 6. So we need 12 here. So all that goes there is a 6. So now we have a balanced chemical equation. Okay? Now, as it pertains to stoichiometry, the expectation is for you to be able to convert mass to amount produced. And we're going to come back and do that after we talk about that in the lecture material. And we're going to do B and C as well once we get to that. Okay, so empirical formulas are the lowest whole number ratio of atoms in a particular chemical formula, but that does not mean that it is your molecular formula, right? Some molecules have formulas that can be reduced to lower whole number ratios, but the empirical formula can always be determined from the percent composition. And we have some examples of that in our in-class worksheet that we're going to talk about. But if you know the mass percent in elements, then we always assume a 100-gram sample of elements that we're dealing with. We then determine, we take that, convert the percent into grams of each element, we convert that to moles of each element, and then we look at the mole ratio to find the empirical formula. Now, you will see this process in the in-class worksheet step by step. Here, they show you, this is example using para-aminobenzoic acid. We have the percent composition of carbon, hydrogen, nitrogen, and oxygen, and we want to know the empirical formula. So what they do is they convert each of these, assuming a 100-gram sample, into grams. We do a dimensional analysis of the molar mass to get moles, and then we take the lowest number of moles and divide that into the rest, and we see that we end up with ratios of 7, 7, 1, and 2. And that will give us an empirical formula of C7H7NO2. And again, we're going to do this in our example as well. Now, after you have an empirical formula, you may be asked to determine a molecular formula, and the molecular formula has to be a whole number multiple of an empirical formula. Why? Because you can't have half of an atom, right? You can't have half an atom. So it's always going to be whole numbers. If we find the empirical formula and we have been given a molecular weight for the compound that we're interested in, we can always find the molecular formula by a division. So here, the empirical formula was CH, but it has a molar mass of 78. So if we look at the molar mass of CH alone, it's 13. We've been given the molar mass of the molecule as 78. If we divide 78 by 13, we end up with 6. So we multiply each of the atoms involved in our example by 6, and we end up with C6H6, which is benzene. We won't be worrying about combustion analysis. I did not give you, I don't think, examples of that in the in-class worksheet. If there are any examples, you will find them in the Workout Wednesday. If there are any in the homework, you should be able to utilize the Workout Wednesday to use those. Okay, so really quickly, let's take a look and at our in-class worksheet, and we'll go through a couple examples here as it pertains to percent composition. So aluminum chloride, you could have searched this, or you could have remembered that chloride is going to be ClO2 -1, and aluminum is always Al3+, right? So if that's the case, then our compound is aluminum ClO2, and we need 3 of them, right? We need 3 of them to create a balanced, zero charge, empirically formulated ionic compound. Now, if we look at the math here, and we want to know the molecular weight is equal to 1 times 26.98 grams per mole, which is for aluminum, plus 3 times 35.45 grams per mole, and that's for chlorine, plus 6 times 16 grams per mole, and again, that's for oxygen. And that number gives us 229.33 grams per mole for the molecule, right? That's for our aluminum chloride. But we have been asked the percent composition of all atoms, so we need to do the math on all of these. So if we do the math on aluminum, we see percent aluminum is equal to 26.98 all over 229.33 times 100, and that is equal to 11.76%. Chlorine is equal to 106.35 over 229.33, and that's all times 100. And again, you can put your parentheses here so you don't forget, and that's going to be equal to 46.37%. Now, somebody might ask, where did this 106 come from? I don't see it anywhere. This 106 is the product of this multiplication here. So just make sure that, remember, percent composition is total mass of that element over the total mass of the compound. And then lastly, percent oxygen is equal to 96, which is also the product of this multiplication, all over 229.33 times 100. And that is equal to 41.86%. And that would be how to solve just a basic percent composition question for a compound. Okay. Next question. This is a empirical molecular formula question. So they tell us that a white powder is found to contain 43.64% phosphorus, 56.56% oxygen, and they've given us the molar mass of the compound is 283.88 grams per mole. They want to know empirical molecular formula and the name. So, first thing we do is we assume 100 grams. Therefore, we're dealing with 43.64 grams of phosphorus. We might as well go ahead and convert that to moles since we know we're going to need that. 30.97 grams of phosphorus per 1 mole. Remember, I got this value from the periodic table. This is equal to 1.409 moles of phosphorus. Now, if we do the same process for oxygen, 56.56 grams of oxygen, we know that 1 mole of oxygen is 16 grams of oxygen, also from the periodic table. And this value ends up being 3.535 moles of oxygen. Remember, we take the smallest number of moles and we divide it into both. We end up 1.409 divided by 1.409, and we end up with 1 mole of phosphorus and 2.5 moles of oxygen. We cannot have a empirical formula, remember, with a half of a mole. All empirical formulas have to be whole numbers. So to get a whole number out of this ratio, we need to multiply both of them by 2. So we get a multiplication by 2, and we end up with 2 moles of phosphorus and 5 moles of oxygen. And hopefully we see that. If you ever end up with a half of a mole or 0.33 of a mole, you need to multiply to get you a whole number. So the empirical formula is 2 moles of P, 5 moles of O. Therefore, the empirical is equal to P2O5. Okay? And if we wanted to look at the empirical formula of molecular weight, we find that molecular weight is equal to 141.94 grams per mole. And you can pause the video here and convince yourself that you can do that calculation. Well, if we look at the 283.88 and 141.94, the molecular formula can be determined by dividing 283.88 all over 141.94, and this is equal to approximately 2. So therefore, the molecular formula is P4H10, sorry, O10, not H, P4O10, and the name of this would be tetraphosphorus decoxide, right? If we remember our rules for covalent compounds, okay? So that's a great question from top to bottom, determination of empirical molecular formula and throwing in some nomenclature for you there. Throwing in some nomenclature. Okay. Question 3, also a empirical formula question. They tell you the molecular mass is approximately 100 grams per mole, and they give you a 10-gram sample that contains chlorine, carbon, and hydrogen. So we do this exact same process. The empirical formula here ends up being, and I'm going to let you do this work, but I'm going to give you the answers. The empirical formula here ends up being H2CO, and then the molecular formula ends up being H6C3O3. But convince yourself for this and try that out on your own and see if you can get those two answers. Okay. Now, quantitative information from a balanced equation is going back into our stoichiometry, and we're going to go back into the question that was about theoretical yield. The coefficients in a balanced equation show the relative number of reactants and products, and it will also allow you to convert that into mass, depending on how much you are going to form or how much you are going to use. So stoichiometric calculations using a chemical reaction are usually started with a grams of a substance, whether it be a product or a reactant. It doesn't have to be one or the other. It can be either. You can then use the molar mass of that substance to find out the number of moles. You can then use the coefficients from the balanced chemical equation to convert into moles of another substance, and then utilization of the molar mass of that substance, you can find out how many grams should be produced in theory, right? And it's very important to know that this is in theory, because in practice, in the laboratory, in the in the industrial situation, we do not always get the exact amount because 100% efficiency is what all engineers strive for, right? And that's what most of the research on chemical reactions for large scale, that's what it's done on. How can we increase efficiency, save money? So the mole ratio comes from the balance coefficients in the equation, and this is the kind of calculation that we're going to do in our particular problem on the first page. So they use a glucose combustion, and they want to know how much water is produced. They start with 1 gram of glucose, and as you can see here, their molar mass or molecular weight is 1 mole for every 180. They've converted that to moles. They've then used the mole to mole ratio in the balanced chemical equation here, right? 6 to 1. That we get 6 moles of water per 1, and then we can use the molar mass of water, 18 grams for every 1. This gives the answer, and they've done this step by step by step. You'll see me write this very similarly, but I'm going to just do it in the kind of boxes that you see in my dimensional analysis. So let's go back to page 1, and let's take a look at the amounts of products for this particular reaction. So we balanced the chemical equation already, but now let's take a look at the stoichiometry. The stoichiometry involved says we want to find out amount of all products formed, but we were given 900 kilograms. Okay, so with 900 kilograms, we'll start, and I'll just abbreviate this as glucose, and we need to convert to grams. Why? Because grams is what our molar mass is going to be in. So to get the molar mass of glucose, we just saw that in our example, 180 grams. So 180 grams, and again, that's approximate. 180 grams of glucose per 1 mole. And if we want both products, let's just start with CO2. We got 6 moles of CO2 per 1 mole of glucose. And then if we want to know the molar mass of CO2, we do that calculation. We see it's 44.01 grams of CO2 per 1 mole. So now we have the entire dimensional analysis for amount of CO2 produced, right? And that number is 2.38 times 10 to the 8 grams. Okay? Now, this process is exactly the same for determination of water, except our ratio here should be moles of water per moles of glucose, and our molar mass should be water per mole of grams of water per mole of water. So everything up until this point is all the same. All of this is the same. So I'm not going to rewrite that. But we're going to have 6 moles of water per 1 mole of water, and we're going to have 18.02 grams of water per 1 mole of water. I am going to always suggest to use all of your units and labels so that you do not get confused, so that you can go back and double check, and if you ever do make a mistake, you can find out where that mistake is. And for water, it's going to be 9.37 times 10 to the 7 grams of H2O. And so that is the stoichiometry that they have asked us for. Theoretical yield. That's what both of these are. Theoretical yield if we were to burn all of the glucose, every last molecule. Okay, now part C talks about percent yield, and percent yield is just actual over theoretical times 100, right? Actual over theoretical times 100. So therefore, the actual is 30 kilograms, or 3.0 times 10 to the 4 grams, and we can put all of that over 2.38 times 10 to the 8 grams times 100. And if we do the math on that, we see that we've actually only had a percent yield of 0.01%, right, which is extremely terrible. This is extremely inefficient process, whatever we are doing for this particular combustion reaction. So that takes care of all of the work as it pertains to percent composition and empirical formula on our particular worksheet. Now, in the PowerPoint, we see that heat does not appear in our balanced chemical equation, but when we get into chapter 5, you're going to start to see how the endothermic and exothermic nature of chemical reactions is taken care of when we write out our chemical reactions. They are also proportional to our stoichiometry as well. The amount of heat released is all a function of a balanced chemical equation. It is proportional as well. We won't talk just yet about limiting reactants. We don't have that particular workout in our in-class worksheet, but you will see this in your homework, and you will see this on your workout Wednesdays. And so go check your workout Wednesdays for working on limiting reagent problem. But limiting reactant problem is determining which one of your chemicals will run out first, and it is a function of the amount that you start with and the stoichiometry. And we already just talked about theoretical yield. We showed that in this last question, and we talked about percent yield. So that'll be it for our chapter 3 video and in-class worksheet. Again, if you have any questions, be sure to send me an email. Double check all of your Workout Wednesday videos. You can also go back and check some of your simple stoichiometry videos from our Intro Chem course and some of my Intro Chem videos. And if there's something that you do not feel that has been covered in a video, please just let me know, and we can make another video for that. All right.